Alright, continuing with this series of videos, examining how conventional physics is presented, taught, the theory, and challenging some of the ideas, some of the vaguely presented explanations, and they are merely vaguely touched upon as maybe rules more than some explanation of exactly causes. So I thought we would go over some of the stuff we've sort of learned through doing these videos, in that we've been challenged to explain certain subtle aspects of how electricity manifests itself into magnetism. So I thought it would be a good idea to go over some of what has been deduced. What facts you have to sort of meet. So there's this idea of resistance in a conductor. Then there's also this idea that there seems to be a connection between whatever effects you have of a magnetic effect or a charge effect really being on the surfaces of conductors more than on the interior. But then again, you have resistance, which sort of indicates that the current must be going through the wire, or else you could just gold plate a wire and therefore make it gold throughout, and you can't really do that. You can help by gold plating, but you're not going to change the fundamental quality of the conductor. So I thought I'd explain how some of that might be possible, and how you do end up with polarization in what are shapes that appear to have no polarization. So the idea is, let's try a conductor in a couple of different ways, I suppose. It's always typically kind of round. And the idea is that the surface, so if you were to look at it cross section, and then if you took a piece of the round part, to view what is happening on the surface. Don't know exactly how I want to dimensionalize this, but so that's the surface. Well, the surface would just be a slice, so a slice out of the conductor, and the idea would be is that it is creating little magnets across this surface, in the sense that there's a matrix or an aspect where there is a polarization, like a magnet. A bunch of little magnets add up to a magnet kind of thing. And that isn't very, not enough light, I suppose. I can't see that very well, but it'll have to do, as they say. So I've attempted to explain in previous videos that what's really happening is the round surface, like here, is the atoms aren't playing round. They're playing flat, straight. And so they end up pointing in essentially a direction. A little bit of an edge sticks up. So you could sort of get the idea here. If I can draw it reasonably well. That as they go around, their edges are sticking out. And as they do that, you'd end up having a south pole facing you from the bottom, and which I just drew wrong. And I'll make that red just so you can make sure to see it's red and black. So you could sort of see that the black end is going to have the end of the magnet, the little magnet that is the atom, is going to be facing out and sending stronger radiation in the electron force, and then the red is going to be doing its thing, and so you're essentially creating a polarized round surface. So this round surface would end up being plus at the bottom and minus at the top, no matter which way you rotated it. So from any angle, it'll end up becoming polarized. Just rotate the symbols. So from another angle, this would be plus and minus, and so it just polarizes the conductor. So the interior, I would argue, is something like if say this was a the current's going a certain direction, then the positive ions, the weak ions, would be on the outside versus the inside. And so really what you're deciding is whether the positive or the negative ions are on the inside, and the negative ones would be on the outside, or vice versa, depending on which way the current's going. And so that's the right-hand rule, is there is a certain rule about which way it tends to go, like there's a certain rule about which way water goes in a toilet, for example. And so the idea is that the pressure, the interior atoms, can't expand and contract, can't ionize really, can't, they have to stay at a 4. So the idea would be a positive ion would be a 3, the neutral would be a 4, and then the negative would be a 5, in terms of an extra electron, if you want to think of it that way. But I'd almost argue they don't have to be an actual extra electron, just has to be a change in the pressure. But regardless of whether there's an actual extra electron or not an extra electron, I'd say, I guess, just because of the motion of the electrons, the drift, they probably have to have extras. The point would be is the pressure on the inside of the conductor it just goes like, they just transfer in the sense that they're almost connected atoms. So they almost are, the 3 atom is bound to the 5 atom, so to speak. And so they're both 4 atoms technically, but they just do a little separation to say, okay, I'm 3, I'm 5. And then it's, this one over here is 3 and it becomes a 5. And then this one over here is 3 and it becomes a 5. So the pressure migrates from the center of the conductor out to the edges of the conductor, and is realized in that these exterior atoms are the ones that expand and contract in size to realize the changes in the pressure. So the interior atoms basically are part of the conductor. They're transmitting some of the pressure, but they're pushing the pressure essentially to the outside atoms, and they're the ones that are changing more rapidly, switching back and forth between 3, 5, 3, 5 to transmit the pressure, and are transmitting it through this subtle mechanism of the fact that they're connected by these ions, the dipoles. And so essentially the electricity as it's going through might look something like, because if it's the current's going one way, the positive ions are on the outside, the current's going the other way, the negative ions are on the outside, and what you basically have is that's just on the surface. So it's when I say outside, I mean it's just a circumstance like this. This is your surface, and then this would be in between them but lower. So the proton would be in, the electrons would be out, vice versa, the proton would be out. The proton heavy atom would be on the outside, and the electron heavy would be on the inside. So you just reverse it either way. And so essentially the current flows, the pressure moves through those ions. It won't be moving this way around the conductor. I'm just using this for an example. It's really going in and out if this is a cross-section of the conductor. But the idea is the pressure is essentially moving from the ions. It's converting a 5 into a 3, and a 3 into a 5, and a 3 into a 5, a 3 into a 5, 3 into a 5, in this manner, except going this way. So it's moving in a direction through the wire, either in or out, and just transferring, just switching from 3 to 5, 3 to 5, 3 to 5, over here, 3 to 5. So it's just taking a low pressure atom, converting it into a high pressure atom, and if things calm down, they'll just turn back into 4s and 4. So it's just this, I'm just using the number 8 arbitrarily, but I'm just saying that that's what would be the total, and there's different ways to manifest it, 3 and 5, or 5 and 3, or 4 and 4. And so when a conductor's moving electricity, it's all 3 and 5s on the surface. When it's not moving electricity, it's 4, 4, 4, 4, 4, 4, 4 around the surface of the conductor. So the electricity polarizes the atoms. They polarize in this configuration, and this configuration ends up creating, although this magnet is oriented plus minus, it ends up being minus plus, in the sense that the electron energy is going to be the strong one coming from the periphery. So in spite of what it appears to be its orientation, that's why the two conductors with the same polarization end up doing what they're not supposed to do, which is attracting. Sames aren't supposed to attract, and that happens because of this little extra that pushes that out. And that's why you need very high currents to manifest some of this, is because it's not a very strong magnetism. It's fairly weak. And the way you can strengthen it is to coil a bunch of wires on top of each other, and then the interior of that coil ends up being strong because there's lots of internal reflections. But the outside shows the real weakness. There's very little magnetism on the outside of a coil conductor. So out here there's almost nothing, and in here it's very strong. Well, in here is a bunch of internal reflections. Out here there's the natural state of how much magnetism you're actually creating, which is a very small amount. But when you magnify it by forcing it, trapping it inside a coil. Alright, so I think that's enough just to say where we are now, and that is, this is all stuff that I didn't have I had elements of this, but I didn't have it kind of all figured out before doing these lectures. So it was a really good idea, in my opinion, for me to invest the time in re-watching the lectures and attempting to provide alternative explanations. Now, some of the things I've said in some of these videos I would like to retract. I'd like to redo them because some of them were wrong-headed, but a lot of it's generated some productive, in my opinion, thinking, and I think this explanation is quite good. I think it's darn close to the truth. So off to the video we go. Hi ho, hi ho, and hopefully without any complications. So we're moving on to lecture 14.
When we have a current going through a wire like so, and we look at the magnetic field in the vicinity of this wire, then we know from experiment that if you put pieces of magnetite around the wire, that they line up in a circle.
Right, so they go around the periphery pointing north-south. So as I pointed out with that circle, the water wheel. So think of it as a water wheel, and you see more of the buckets this way, coming at you, and buckets retracting, and those are two different color buckets. So the ones coming at you are one kind of bucket. The buckets leaving are the other kind of bucket, and that essentially is the polarization. And you don't see the buckets on their side, so you just have to kind of pretend that the side buckets are moot, and that the only buckets that really matter are the buckets coming towards you and the buckets going away from you, and that creates the dipole of the magnetism. And obviously, no matter where you turned around the water wheel, that same effect is happening. There's buckets moving towards you and buckets moving away from you, and those are the ones that have where the magnet is pointing at you. So you're not looking at its dipole side, which is mixed. You're instead just looking at a north or a south. I suppose it could, no, it really couldn't be illustrated that way. Yeah, the water wheel is a bad example in the sense that the buckets are loose, so they don't polarize, in the sense that if it was this hard thing, then it would come at you and you painted it north and south, then you'd see that it switches when it goes down to the bottom. The south and the north switch. But a water wheel, the bucket doesn't switch because it's just hangs by gravity. So it's a little different.
Put it around like this. If that circle has a radius r, then the magnetic field, that's an experimental fact, is proportional with the current I, and it's inversely proportional with the radius of that circle. By convention, the direction of the magnetic field is given by the right-hand corkscrew. Rotate this way, the current goes up.
So that's the R rule in terms of how it degrades. It doesn't tell you how strong it is to start with. So the point is that when you're creating magnetism with electricity, it's kind of weak. Okay, when unless you find some way to magnify it. So it's weak light that comes off the wire. You could think of it that way. But inside, where the light is getting reflected, you can understand that the inside would be very bright and the outside would be very dull because the inside is trapping the light and the outside isn't.
You've seen before with electric charges, when you have a wire which is uniformly distributed, say with positive charge, you've also seen that electric fields in the vicinity of that straight wire falls off as 1 over r. Where the direction is different than the magnetic field, but it also falls off as 1 over r. And the reason is...
it's not different in the sense that the only effect is a change in the proportion of this electron energy versus proton energy, and it just has to do with what the surface is doing. So, as I pointed out, as these buckets change color, as the surface becomes covered with 3s and 5s, there's either more 5s on the surface and 3s in the back, and that becomes a magnet that would be North Pole heavy, and vice versa. But that's really the only effect. This idea of there being a field moving with the current there's no field moving with the current. You're just moving the magnets, essentially. So when a current's moving, it's essentially moving the magnets. It's moving the charge, because as it goes through, it's cycling. So you can sort of understand that the 3 is here, and then the 3's here, and then the 3's here, and then the 3's here, or the 5. So the charge is moving through the conductor in the direction of the current, if you can get it. So it's going, it's coming right for you, the magnet. So it's essentially creating little magnets, and they're little magnets, unlike a regular magnet, these magnets are moving, in the sense that the 3-5-3-5 ratio keeps moving. It keeps moving. It's drifting, like a group velocity in wave functions.
That electric monopoles, individual charges, the electric field falls off as 1 over r squared. And so when you integrate that out over a straight wire, you get the 1 over r field. So by analogy, it would be very plausible that if you took magnetic monopoles.
So this gets a little complicated, but obviously he's sort of pointing out that when you're in proximity to the wire, it's 1 over r because you're exposed to all parts of the wire, and when you get a distance from the wire, it's r squared, because now this is sort of a point charge, and you're not getting full exposure. So it's a subtle difference, but kind of important, about what your exposure is. So it's only 1 over r close. It's 1 over r squared at a distance when it comes to a dipole. And so then he's going to talk about monopoles again. So the monopoles do exist. They are the electron and the proton. They're the thing creating the little magnets. And as you move the electrons through a conductor, you're essentially changing their dipole relationship. So you're making a new magnet in a sense. You're making new little atoms in a sense, because the electron is moving from one atom to another atom to another atom to another atom. So in a sense, that's the movement of the magnet itself, or in a sense, that's the movement of the atom itself. You're moving parts of it, and from the universe's perspective, it can't tell the difference between moving the whole atom and moving the face of the atom. So it's like my face sliding off, and a new face pops on. 3 face, 5 face, 3 face. I'm still sitting in the chair, but my face is going somewhere. Look, you look for it. My brain grabbed that as an analogy. I don't know why.
That the magnetic field would also fall off as 1 over r squared. But magnetic monopoles, as far as we know, don't exist. In principle, they could exist, but we've never seen one. And if any one of you...
See, it's just, you would clearly be a Nobel Prize. I mean, it's just kind of ironic. It's sitting there right in front of them. I mean, it's clear that the electron and the proton are the monopoles of magnetism. They'll even do experiments where they talk about domains moving and the atoms aligning as ions, and yet they'll sit there and say they don't know what the magnetic monopoles are. Clearly, the magnetic monopoles are protons and electrons, and the only thing they're missing is an understanding that there's a force and that the force is also polarized. And that's what makes it all work. But they're right there in front of them. Even without the force, which is incredibly important, but I'm just saying, even without it, they should be able to, even without it, I was already convinced 20 years ago that electrons and protons were magnetic monopoles, in the sense that that's how you made a magnet, was aligning those monopoles into a dipole. The dipole is the magnet. Having one of each one is the magnet. So I don't know how you can't draw the conclusion that those are the dipole, the monopoles.
We have to find one. That would certainly be the Nobel Prize. It's by no means impossible. And so the simple fact that the magnetic field around a current wire falls off as 1 over r sort of suggests that if you carve this wire up in little elements dl, that each one of those elements contributes to the magnetic field.
All right, so understand. So from that picture, so the current's going this way through the wire. The little magnets are lining up this way, and they're going to move their little magnets up the wire this way with the current. So there's a little magnet, and it's going to move this way, and it's going to move this way. So it has north-south, north-south, north-south as a perimeter, and as I pointed out, you can see the north-south thing in the sense that there's buckets coming towards you and buckets going away from you. They don't have to be turning this way, so I didn't want to imply they're turning. I'm just saying when they sit on a curved surface, they'll go flat. So you can understand that on a round surface, they're doing this flat thing. And the flat thing means their edges are going to keep popping up. They're going to have a sawtoothness to them. And that sawtoothness is creating the polar energy, the very strong force is coming out of the end of the magnet. The strongest force comes out of the north-south ends. So the strong force is the one that's going to be felt. And the strong red force. So strong black force here, strong red force here. But there's nothing moving this way. The current's moving through the wire. So if the wire's this way, the current's going through the wire. The magnets are arranged this way and this way. They're going red, black, red, black, red, black up the wire. They're going red, black, around the circumference of the wire. But the only red blacks that are moving up the wire or down the wire.
In an inverse r square law. And by integrating out over the whole wire, you then get the 1 over r field. And this is behind the idea of the formalism by Biot and Savart, who introduced the idea that if you have a little current element, dl, and the current is in this direction, and you want to know what the magnetic field is, it's a small contribution dB to that little current element, and the distance is r, and the unit vector from the element dl to the point where you want to know the magnetic field is r roof, then the idea is that dB is a little bit of magnetic field. In this case it would be in the blackboard because of the right hand corkscrew rule. Current is in this direction, so this little element would contribute to a magnetic field in this direction perpendicular to the blackboard. It's some constant proportional to the current, no doubt, and then it's proportional to the length of that little element dl. If it's longer, then magnetic field is larger. And in order to get the direction right, perpendicular to the blackboard, you take the cross product with the unit vector r. The unit vector.
Right. So that's just the right-hand rule is the little hat r, just to point out it goes a certain way by convention, by the rules of swirling water or moving charges. They have a rule as to which way they swirl, but they're not really swirling. I don't know if there's much to say about this. Again, this just has to do with a way of figuring out whether you're close or far. Whether you're close to the charge elements, or whether, you know, the monopoles, so to speak, or whether you're far enough away that all you see is dipoles.
Vector r has length 1, so you only do that in order to get the direction right. And then inversely proportional to r squared. That's of course key. And this is the formalism by Biot-Savart. And you can do experiments and measure the magnetic field in the vicinity of wires. And this formalism works. So you then calculate the individual contributions of all these little elements dl, and then you do an integration, and this formalism works. You can then also measure what C is in SI units.
The other part of it is a wire is a linear thing, okay, and so it can't do it's not a sphere, so it's only like one plane, and so you're going to have it drop off as 1 over r because you're only feeling the effect from one plane rather than from two that are going out this way. So if something's spreading in both directions, it's diluting in 2 dimensions, but if it's only going in 1 dimension, then it can only dilute in 1 dimension. So it's, I don't know, a good analogy for that. It's if I took one laser beam and moved it up and down, you could figure there'd be so much light that's going to hit areas, and it's going to be a pretty strong light on this straight line that I'm moving up and down in. But then if I start to move it also this way in the same amount of time, that is, I go this way, and then go up and down, and then go this way and this way, you can understand that this way and this way is going to get a lot less light, because now I'm going this way and this way. And this way and this way is going to get a lot more light than the zero before. You know, there was zero light going this way before. And I'm doing it in the same amount of time. So obviously the only place those photons can come from is the photons that were going this way. So it just really has to do with the r squared applies to surfaces. R applies to wires, because wires are only, they're not spreading in the same there's not the same inverse over a width. There's just the width of the wire, which is tiny relative to the spread of the field. So these, I would argue that applying these rules are approximations at best, because the subtlety is in the fact that it matters how much surface is producing the field, and dl doesn't tell you how much surface there is to the wire. Now the r of the wire does, but like I said, at a distance it's going to definitely, the wire looks longer than it is wide. So there's a clear, as soon as you get a distance from that wire, you're going to see that the wire's longer than it is wide. It's not a sphere anymore. Up close it can look like a sphere. Far away it's a wire. I mean, it's a very stretched sphere.
C is 10 to the minus 7, but we write for C something quite peculiar. We write for C mu 0 divided by 4 pi, and we call this mu 0.
Right, which is just insanely irritating. That they would take a number, a constant, and then they replace it with something as bizarre as mu 0 divided by 4 pi, just to make a mess out of it. I mean, just to make it incomprehensible. So you just take the number 58, and then you turn it into mu 0 over 4 pi. And, you know, you're sort of arguing, all right, well, that's where mathematics goes up its own butt. You know, that's where it's going. Why would you do that? It's a number, it's a constant. It's already in its simplest form, and now you're putting it in a more complex form. You're not simplifying it, you're complicating it. And that's the wrong direction. And that makes it look like a gimmick.
The permeability of free space. You've seen earlier with Coulomb's law that this constant 9 times 10 to the 9th, we call that 1 over 4 pi epsilon 0. What is in the name? And so
no, it's not just a name. I mean, it's taking something in its simplest form and somehow dressing it up as something else in a costume. And you're saying, why is it in the costume? And the obvious argument would be, why are the people going to the bank wearing hoods over their face? Ski masks and hoodies. You have to ask the question, why are they doing that? Well, they're not doing that for some good purpose. They're doing that for some trick purpose. And that's all I see there is, when you take constants, you take quantities that are in their simplest form and just dress them up for no reason. I could make that into any kind of relationship that gives me the same number. So I could go and find the density of oxygen in the atmosphere divided by the hardness of rocks, and I might be able to come up with a number that's about the same ratio, 6 point something to the 10th power. So I could come up with any idiotic two things that equal that number and say, there, that's important. When, no, that's a contrivance.
here, we call this mu 0 divided by 4 pi. So now you can apply Biot-Savart's law, and you can go to a straight wire, and you have a current I, and suppose you want to know what the magnetic field at that location P is, at a distance capital R.
So understand, at P, okay, the wire's this big. So it's a little piece of wire. I mean at the point where he's taking the cross section of the wire, and certainly the width and the thickness of the wire would be it could be the same if you just cut a little distance out. That little hunk can only produce so much force, where the whole wire is going to have a lot more because it's going to create energy. Is going to be coming from more than one direction.
And so what you now have to do is you carve this up in an infinite number of small elements dl, and this distance is r, and the unit vector is then like so, and you calculate the small amount of magnetic field due to this little element, and you integrate this over the whole wire. It's mathematics. You've done it. You've done it before, where we had uniformly electric charge on the wire. So I'm not going to do this again for you. It's a very...
Right, and the two sides even out, of course. But again, it's just linear. It's only in one dimension, where with some other surface, it's happening in both dimensions. It's getting wider in both.
Very straightforward piece of mathematics. The magnetic field, by the way, in this case would come out of the blackboard, because of the right-hand corkscrew rule. And what you find when you do this, you will find that B equals mu 0 times I divided by 2 pi r. This being r, and so you indeed see that the inverse 1 over r comes out. And so if you, for instance, take a radius of 0.1 meters, 10 centimeters, and you have a current through the wire of about 100 amperes, then you would end up with a B field, if you use this equation, 2 times 10 to the minus 4 Tesla. That is about 2 Gauss. 100 amperes, 10 centimeter distance is only 2 Gauss. Think about it, the Earth's magnetic field is half a Gauss. So if you go 1 meter away from the wire, so you have a magnetic field which is 10 times lower, but look, it goes 1 over r, then the magnetic field of the Earth already dominates substantially. So you need very high current actually when you do these experiments.
Right, but we can obviously create an awful lot of magnetism with just a little tiny wire, just coiled. So as soon as you coil it, again like the light analogy, the light inside the coil doesn't escape. And so like a laser, it just magnifies and magnifies and magnifies. It stores up all that light. and that is what's creating much more magnetism inside. And so if you stick a piece of iron or something in there, you're really going to be taking advantage of a lot more exposure to energy that's going to magnetize the iron.
It's nice to see that out of Biot-Savart's formalism, the 1 over R pops out, but of course you must realize that Biot-Savart knew that.
It is surprising when they switch to the audience how many Asians, or even back in 2005, dominate like half the class.
The magnetic field falls off as 1 over R. It was an experimental fact. So the fact that it falls out is logical because we're cooked into that formalism. If you think about it, it all goes back to Newton. Newton was the one who first suggested that the gravitational field falls off as 1 over R squared. And then later, a logical extension was that the electric fields would fall off as 1 over R squared. And out of that came the idea that the fields of magnetic monopole, if they only existed, would fall off as 1 over R squared. And that's all behind this. And so
it's also, I'm thinking about the Asian thing still. It's just funny how they haven't really migrated, though, into teaching or talking headery or theoretical physics. You just don't see them, the end product. So they're probably doing all the engineering and working on the guns and the machines of physics, but they're not doing any of the periphery of physics.
The person who really deserves most of the credit for all this in my book is Newton. Using Biot-Savart, we can calculate now quite easily the magnetic field.
So again, it's all just about calculating some kind of field rather than understanding what's causing the field. And so, again, my critique would be this is the huge failure of physics, is giving up on causes and just focusing on analyzing effects to death.
At the center of a current loop, let this be a wire, circle, and let the current go in this direction. And I would ask you, what is the magnetic field right at the center? Well, the magnetic field right at the center, of course, is pointing upwards. Each little element along the line here, dl, each little element will contribute a little bit magnetic field at that point right in this direction.
So understand, though, is if you put more and more of those wires, and again, the interior, it just keeps on affecting it. It just keeps bouncing in there for a very long time. So it doesn't create one little burst of energy. It bounces back and does it again, and then bounces back and does it again. So again, it's like me. I have to try to think of some better analogy. But if I had X-ray vision and there was a mirror and I was a mirror to it, well, you could just see that the X-rays, instead of going into the universe, would bounce off the mirror and then bounce off me and then bounce off me. And so as I keep producing them, they're going to keep multiplying and multiplying and multiplying. Now there's a certain limit to that, and that there's some escape, but I'm just saying that's what you're gaining, is a point of equilibrium, and then the most you can actually magnify the effect. So there's only a certain amount of pressure you can build up with those extra impacts, but those extra impacts are going to make a tiny force a very powerful force. So as soon as you start coiling the wire, you take what he described before as a very weak force, 3 times 10 to the 4th Tesla or whatever, into a much stronger force.
If this radius is r, with Biot-Savart now, we can calculate quite easily the total field that you would get at this location. Because that total field is then the integral of dB vectorially over the entire wire, so the entire loop. So if you go there, so you would get your mu 0 divided by 4 pi, you get your current, and you get your 1 over r squared, and now you have to do an integral over that dl cross r. Well, r is of course always perpendicular to dl. Any element dl that you choose, the unit vector r is exactly perpendicular to the element dl, because that's a characteristic of a circle. And so the sine of the angle between dl and r is 1. And so all we have to do is do an integral over dl, which is the integral of this circle, which is the circumference of the circle, and that is 2 pi r. And so now you find, lose a pi, you lose an r, so you find mu 0 times I divided by 2r. Just to show you an example, how in this case, how easy.
So now you just have the permutivity of space times the amount of current, so it's a constant times the current, and the constant is a small number, and divided by r squared. Well, anyway, continuing.
It is to use Biot-Savart and calculate the magnetic field right at the center. If you were asked what the magnetic field was here or there, that would be also relatively easy. You've done that. I've given you a problem earlier where we had point charges uniformly distributed on a wire, and I asked you what the electric field was here. So that can also be done now with magnetic fields. If I ever asked you what the magnetic field would be here, that of course is an impossibility.
All this stuff
with Biot-Savart. Practically.
All this will look, it looks at the same as when he's describing the electric field, and the only thing that really ever changes is that r squared versus r number are, but it's all the same thing. So again, it's just this contrivance that these are two different forces when they're the same force. There's no difference between an electric effect that moves something and a magnetic effect, except the difference of dipoles versus monopoles. That is, the monopoles of positive charge and negative charge being able to break the battery, the magnet, into monopoles. But that's really it.
Possibility. I wouldn't know how to do that. But in principle it could be done, and certainly with a computer you can do it. So we can go to our same situation, we can take...
So he says he doesn't know how to do that, but obviously it's the same mathematics. You're just picking 2 points. Again, you just pick average points. So you take the left point, the right point, the point to where it's right above you, and then the point where it's furthest distance. And if you figure out those 4 points and just average over a circle, you probably get your answer. That's pretty darn close.
100 amperes for I, and you can take R 0.1 meters, and then the B field, the strength of the B field right at the center of this loop that I found is then 6 times 10 to the minus 4 Tesla. And that would be 6 Gauss. It's clear that if you want to put in some field lines, magnetic field lines, as a result of this current going around in a circle, that through the center there would be a field line like so. If you're very close to the wire here, which goes into the blackboard, I want you to see this 3-dimensionally, then the magnetic field will go like this, clockwise. Here the current comes to you, so it will be counterclockwise.
So again, he's using clockwise and counterclockwise to point out really positive and negative. So yeah, from one side you're going to see more red energy, from one side you're going to see more black energy, is what he's basically saying. But there's nothing spinning. There's no clockwise and counterclockwise. They're just using clockwise and counterclockwise to identify whether it's north or south. Force, plus or minus force, positive or negative charge.
If the magnetic field line is here like so, and here it is curled up, then clearly I expect them to be here, sort of like so, and like so, and like so. This is the kind of magnetic field line configuration that I would expect then in the vicinity of
dissimilar charges. So those are the field lines for two same charges, because you're going clockwise over here and counterclockwise over here, so you're showing the same magnetic profile across that interior. The two arrows are both going away because one's going clockwise and one's going counterclockwise. So one is showing red end going away this way, and the other was showing red end going away this way. So it's essentially having two magnets that are the same poles, and so it's a repelling force between them.
Such a current loop. And I want to show this to you in a little
Repelling meaning more reflections than absorptions.
bit more detail. I have here the transparency, and you see there on the right side the current goes into the paper, and here it comes out of the paper. It is a circular loop, and you see here the field line configuration. It's not too different from what I have on the blackboard there. Very close to the wires, of course, you get circles, because the 1 over r dominates there. You're so close to the wire that the 1 over r relationship makes it come out like circles, and here too. But then, if you're farther away, you get configurations like I have there. When you're very far away from a current loop, the magnetic field configuration is very similar to that of an electric dipole.
See, this is the joke. He's got a dipole sitting there, essentially, and he's not recognizing it's a dipole. A compass needle's lining up on it. Compass needles line up on dipoles, primarily. They don't line up. If you have a monopole, it just points right at it. So clearly, it's already a dipole. Of course, it would be seen as a dipole. It's a dipole.
I can show you that in the following way. Let's first look at the electric dipole that you see up there. This is a positive charge, this is a negative charge. Don't look anywhere near the charges. Don't look in between the charges. Look far away. Here you see electric field lines. And you see them here. Now look at your current loop here. The current is going into the paper here, coming out of the paper. It is a loop. And look, you see the same configuration. Field lines, field lines. This goes like so. This one goes like so. Here, the electric field lines coming in. Magnetic field lines are coming in. Electric field lines are going out. Magnetic field lines are going out. They look very similar. Gauss' law tells me that the closed surface integral of the electric flux is the charge inside the box, divided by epsilon zero. And so if you have a closed surface here, it looks like a line, but I meant it to be a surface, then that closed surface integral of the electric flux is not zero, because there's a charge inside the box. No matter where in the magnetic field you make a closed surface, there is never any magnetic flux going through that surface. Never. Unless you come into 26100 and show me a magnetic monopole. Only then will there be magnetic flux coming out of a closed surface.
Well, again, if I could bring an atom in and show you, then I could show you the monopoles, because those are the only true monopoles are going to be the electron and the proton. They're the monopoles. And the only way I can show you a monopole is to show you something that is completely dominated by one or the other. Then it will look like a monopole. So I can put a balloon with, charge on it, and I can say there, it's sort of a monopole. Yes, it's made out of dipoles, but from the outside it looks like a monopole because all the monopoles are on one, or are facing you, or on the surface. So, but those are the only ways you can see it. So short of bringing you an electron and just putting it on the table and saying there's a monopole, but they exist, and we have synthetic versions of them.
If we put the magnetic monopole inside.
And this now brings us to the second of 4 Maxwell's equations. The first one being Gauss' law. The second one is that the closed surface integral of B dot dA is always 0, unless you come with a magnetic monopole.
So we now have 2 of Maxwell's 4 equations in place. Historic day.
This is probably another way of saying that there's always a net amount of force. You can't destroy red force, you can't destroy the black force, so it has to go somewhere. So all you're really doing is, if you draw a circle around something, that's not going to tell you that you have more red energy going this way and more black energy going this way. It's not going to tell you the proportions that are inside that circumstance. So that's all this is really, is a discussion saying, well, anytime I capture a charge that's creating a magnetic effect, that is a ions, disproportionately arranged. Anytime I draw a circle around them, well, yes, I have both of them in there, and I have the same amount of force in there, red and black, but it's really not telling you where it's distributed. It's just telling you if I collect all of it, there's still going to be 50-50 red-black. But it's highly important that all the reds go in this way and this way, and all the blacks go in this way and this way. That's a very important fact, or most of it, or a higher percentage of it. That there's a disproportion about where it's going to hit is really important.
I want to show you the magnetic field in the vicinity of a wire like this. I have to use a few hundred amperes through that wire. I told you why, because magnetic field falls off quite rapidly. And I do that with iron file.
So he wouldn't have to if he just coils the wire, obviously. So he'll get to that eventually, no doubt. But if you coil the wire and magnify the force, then you'll see it much easier with a lot less current.
But I will sprinkle around the wire, and these magnetites will orient themselves in that magnetic field. And then I will try to also make you see this field configuration by having one wire going into the paper and one coming out of the paper. So let's first look at the single current wire. It's coming towards you and it goes into, of course. It is a wire that goes like this, and the reason why you see it here is, of course, we have to get the current in somehow. But it really is a wire like this. And this platform I'm going to show you. So I'm going to put some iron file around this. These are magnetites.
Can't see it yet.
And when they see a magnetic field,
where the wires are
they
going
will
in
try
and
to
out.
orient themselves in the direction of the magnetic field. So you're going to see these circles.
All right, so it's going in one and in the
I
other.
appreciate the fact that you need huge currents for this. Hundreds of amperes we do. That's why we have a car battery here. Remember, that was capable of delivering many hundreds of amperes. So I close the current now. I tap, and you can see the circular configuration. I hope you can see that. Oops.
So that's one wire, and he's just pointing out that all the little filings go around in a circle. And it's obviously not perfect because the wires going across the thing there is also creating fields going this way. So those are disrupting the field where the wire goes in. So the wire probably should come up higher to get a cleaner view. Because this is a little bit, the circle isn't perfect, and it really should be kind of a perfect circle around the center of that wire penetrating the surface. So what else needs to be said about that? So again, that's just an effect. There's nothing swirling around the wire. There's no right hand rule thing spinning. None of that's happening. It's a radial force, and the current is moving through the wire this way, and it's pushing, if it is in a sense moving. It's moving magnets this way. So you're not going to really see the effect of the movement because the magnets they're only on one plane, the little filings. But if you could sort of see it, the filings might want to move along the wire. They might want to. I mean, if you could put them in three-dimensional space, you might be able to see some of that.
Like circles. I want to do the same now, which is a little bit more exciting perhaps, with one wire going into the plane and the other one coming out. Even though it's not a circle, the idea is that you get a field configuration very much like you see there. Oh, it's already hot. These cables are already hot. They don't like the few hundred amperes. Okay, let's do it this way. So you're going to see a field configuration similar to what I have on the blackboard.
See, that staple should be higher. I mean, they should have just made it a little bit higher, just not to distort the effect. Because again, there's current going all the way through, and it's creating magnetic fields that are hitting at the R squared rule. They're weak, but they're still enough to mess it up a little.
Similar to what you have here. Oh no, not this one. Similar to this. Yeah, actually, it was also the one I had, but this is a nicer way to look at it. So we have one wire going in and one wire coming out of the plane.
So opposites and opposites repel. Sorry. They're the same surface. They're both, one's going counterclockwise, one's going clockwise. So that means both have forward facing this way, and both have trailing faces on the other side. That means the dipole is this way, and those two magnets are the same. So it's plus minus plus minus, repelling total.
All right, so let's first put some iron file on.
I don't know why he calls it. No, they're little tiny bugs, but I mean, just he always says iron file. You know, filings, not a file. File is what you make filings with.
All right, and now a few hundred ampere through it. Tap it. And you can see close to the wires that goes in, here and here, you see circles, because of the 1/r relationship. They dominate the magnetic field. But look in between here, there's a little bit of imagination. You can see these field lines go.
You'd see them a lot better if they just had that wire higher. So, just saying.
Going like this, just like I have there on the blackboard. All right. We don't need this anymore, and we don't need that anymore. So this gives you a little bit of insight into the magnetic field configurations that we have about these wires when we run a current through. I will return to magnetic fields next lecture, and we will expand on it. We will learn techniques to calculate magnetic fields in a way which is highly superior to Biot-Savart's law. In fact, that will get us to the third Maxwell equation, almost. But I now want you to relax a little bit, because this may already have been a little rough on you. And so now I want to discuss something entirely different, something very practical, and it has to do with the transport of electric energy. So we have a power station somewhere at location A, and they
I don't know if changing the subject makes much sense, but I guess we'll go a little deeper here. A few more minutes.
deliver electric power, electric energy to Boston. Here is Boston, location B. And A is the location of the power station. This could be 1,000 miles, the distance. There's a cable going from the power station to us. And the potential here in this line is VOP. And here's a cable for the return current. So the current goes like this. And the return current is in this direction. And
It's just a plus minus wire. Obviously return is kind of a dicey word in the sense of alternating current. But anyway, because they both are pushing and pulling, or whatever you want to say. So this is going to come down to this voltage amperage thing. So the argument I would make in explaining it is voltage is the pressure between the electrons, amperage is the number. So in a sense, and you can almost argue that there's a little bit of an association between voltage, pressure, and speed. So how fast the magnets move will be dictated by voltage. But how many magnets move is amperage. So you can sort of understand that how fast they move, that probably doesn't bother the conductor much. The conductor couldn't care less, in a sense, how fast things are moving. They're on a rail, on a train track, and as pointed out, they're all in arrangements, and you're just really talking about how fast they bang into each other. Boop, 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 whether they're going like this or whether they're going like this, doesn't mean much. But the actual part where they're moving, that is, where one atom is transferring with another, the actual number of transfers, that gets more, that's more of an event. And so the amperage is the number involved in the transfer of the pressure, and the pressure is the amount of pressure for each one. So you can understand that if you're only exchanging one gold piece with somebody, it would take a lot of transactions doing one gold piece at a time. But if and you had to do I gotta do 10 to this guy, and then 10 to this guy, and 10, counting out $1 bills, where it'd be so much more efficient just to throw them 100. Give you 100, give you 100. It's only one transaction. So the high pressure is really efficient. It's just $100 bills, and the the low pressure, the single dollar bills at a time to get up to 100 is a lot more taxing, a lot more movement, a lot more energy, a lot more activity. So it's the activity of the conductor is basically the exchange rate. And so if it can exchange $100 bills or $1,000 bills or $10,000 bills, it does a lot less work than if it has to keep exchanging $1 bills. So that's why there's such a huge advantage to moving electricity through a wire at a high voltage, because it's so much less taxing on the wire. The wire doesn't have to do any work. Now the disadvantage is when you get the voltage high enough, then you have this whole breakdown problem where the air is a conductor and the voltage will go through the air and it'll do all kinds of stupid things you don't want it to do. It'll escape in places you don't want it to. But the fact that it's hugely efficient, I mean gigantically more efficient for the conductor to do $10,000 bills than individual dollar bills. Good analogy. I'll give myself an A+. It's a really good analogy. Off the top of my head, good stuff.
And here you use this energy. You hook up your computer, you hook up your hairdryer, your heaters, electric toothbrush, and what have you. Your TV station, everything. And so you're the consumer here. You take the energy that is provided by this power station. I will call the potential of this line 0. And so this is V of A higher than this line here. Well, according to Ohm's law, VA minus VB is the current times capital R, which is now not radius, but that is resistance in the wire. This wire, this cable, however thick it may be, has a finite resistance. And so VB.
So resistance is just a way of saying how that's the ligaments in your arm. That's the, that's what's being taxed every time you have to do this transaction. So the less you're using the resistance is to the motion. So you can just think of you're in a, so you think of it as you're underwater and you're doing these transactions. And I'll give you some effect of how much work every transaction is, because you have to do it in this resistive, confinement. You have to fight the environment to do the transaction. So obviously, the less transactions with the more value, the better.
That is the potential that we receive in Boston equals VA minus IR. So if there's no current going through the wire, no one is using any electric energy, then VB is the same as VA. Now I want to know if we...
It really isn't. I mean, the voltage still exists, whether you are taking it or not. So I can measure the voltage is still there. So that's just not really quite right. But anyway, probably a good place to stop, I think. I'm not really halfway, so we'll go a little bit more. Well, this is a kind of a long video. All right, so we'll call this the place, and we'll just make the other section longer, and such. So till the next time, and I think this is the one of the ones worth watching. Yeah, high value here.